ठीक है। तो हम पढ़ेंगे एक्सरे डिफ्रैक्शन। तो एक्सरे डिफ्रैक्शन है, एक्सरेज आर पार्ट ऑफ द इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम विच आर ऑफ एक्सट्रीमली शॉर्ट वेवलेंथ एंड हाई फ्रीक्वेंसी। एक्सरे हमारे इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम के वो पार्ट है जहाँ पे कि बहुत ही शॉर्ट वेवलेंथ होता है, बहुत ही हाई फ्रीक्वेंसी होता है। एक्सट्रीमली शॉर्ट वेवलेंथ एंड हाई फ्रीक्वेंसी, द लैम्डा रेंज तो वेवलेंथ का जो रेंज होता है वो 0.01 नैनोमीटर से लेके 10 नैनोमीटर तक होता है, और फ्रीक्वेंसी का जो रेंज होता है वो 10⁻16 हर्ट्ज से लेके 10⁻20 हर्ट्ज होता है। और जो एनर्जी होता है एक्सरे में वो होता है 100 इलेक्ट्रॉन वोल्ट से 100 किलो इलेक्ट्रॉन वोल्ट। ओके, X-rays are part of electromagnetic spectrum which are of extremely short wavelength and high frequency। जहाँ पे एक्सरे इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम के उस पार्ट में लाई करते हैं जहाँ की बहुत ही शॉर्ट वेवलेंथ और बहुत ही हाई फ्रीक्वेंसी होता है। वेवलेंथ का रेंज 0.01 नैनोमीटर से 10 नैनोमीटर होता है, और फ्रीक्वेंसी का रेंज 10⁻16 हर्ट्ज से 10⁻20 हर्ट्ज होता है। और जो एनर्जी लाई करता है वो 100 इलेक्ट्रॉन वोल्ट से 100 किलो इलेक्ट्रॉन वोल्ट। एक्सरेज आर प्रोड्यूस्ड व्हेन हाई स्पीड इलेक्ट्रॉन कोलाइड विथ अ मेटल टारगेट। एक्सरेज तब प्रोड्यूस होता है जब हाई स्पीड इलेक्ट्रॉन मेटल टारगेट से कोलाइड करता है। X-rays are produced when high speed electrons collide with a metal target. The loss of energy of the electron due to impact is manifested as X-rays। तो इम्पैक्ट की वजह से जो इलेक्ट्रॉन की एनर्जी लूज़ होती है वो एक्सरे के रूप में मैनिफेस्ट होती है। Okay, the loss of energy of the electron due to impact is manifested as X-rays. Most of the kinetic energy of the electrons striking the target is converted into heat। जो ज़्यादातर जो एनर्जी है जो कि इलेक्ट्रॉन के टारगेट को स्ट्राइक करने से इलेक्ट्रॉन की जो काइनेटिक एनर्जी थी उसमें से ज़्यादातर एनर्जी हीट में कन्वर्ट हो जाती है जब इलेक्ट्रॉन टारगेट को स्ट्राइक करता है, और लेस देन 1% इज ट्रांसफॉर्म्ड इनटू एक्सरेज। और 1% से भी कम काइनेटिक एनर्जी जो था उसका वो 1% से भी कम वाला एक्सरे के रूप में ट्रांसफॉर्म होता है। ओके, फिर भी एक्सरे के पास इतनी ज़्यादा एनर्जी है, 100 मतलब ज़्यादा नहीं है, 100 इलेक्ट्रॉन वोल्ट से 100 किलो इलेक्ट्रॉन वोल्ट होती है इसकी जनरल एनर्जी की रेंज। ओके, अब हम एक्सरे डिफ्रैक्शन की अगर हम बात करें, एटॉमिक प्लेन ऑफ अ क्रिस्टल cause an incident beam of X-rays to interfere with one another as they leave the crystal. This phenomenon is called X-ray diffraction। Okay, the atomic planes of a crystal cause an incident beam of X-rays to interfere with one another as they leave the crystal. This phenomenon is called X-ray diffraction। The X-rays reflecting off to different planes must interfere constructively to form an interference pattern. Otherwise, the X-rays would interfere destructively and form no pattern. To interfere constructively, the difference in path length between the beam reflecting off to atomic planes must be a whole number of wavelength. This leads to the Bragg's law, where Bragg's law is equal to n lambda is equal to 2d sine theta, where d is the distance between the atomic layers, lambda is the wavelength of the incident X-ray beam, and n is an integer. Okay, by observing the interference pattern, the internal structure of the crystal can be deduced. Okay, and then here is the crystal plane, and that X-ray came and reflected like this and transmitted like that, and then another X-ray passed away and then reflected, and then the what is interference is happening. The X-ray reflecting off to different planes must interfere constructively to form an interference pattern. Otherwise, the X-ray would interfere destructively and form no pattern. To interfere constructively, the difference in path length between the beam reflecting off to atomic plane must be a whole number of wavelength. This leads to the Bragg's law. Bragg's law is equal to n lambda is equal to d sine theta, where d is the distance between the atomic planes, lambda is the wavelength of the incident X-ray beam, and n is an integer. By observing the interference pattern, the internal structure of the crystal can be deduced. ठीक है, तो एक्सरे जो डिफरेंट प्लेन से रिफ्लेक्ट हो रही है वो ये आवश्यक होना चाहिए कि उनका इंटरफेरेंस वो कंस्ट्रक्टिवली इंटरफेयर कर रहे हैं और एक इंटरफेरेंस पैटर्न जनरेट कर रहे हैं। अदरवाइज़ क्या होगा कि एक्सरे डिस्ट्रक्टिवली इंटरफेयर करेंगे और कोई भी पैटर्न जनरेट नहीं होगा। अब कंस्ट्रक्टिवली इंटरफेयर करने के लिए जो है वो जो पाथ लेंथ का डिफरेंस होना चाहिए दो एक्सरेज़ के बीच में, वो पाथ लेंथ का डिफरेंस वो क्या होना चाहिए, वेवलेंथ का कोई इंटीग्रल मल्टीपल होना चाहिए। ठीक है, वेवलेंथ का बी अ होल नंबर ऑफ वेवलेंथ, मतलब वही होल नंबर के साथ मल्टीप्लाई करके वेवलेंथ का आना चाहिए वो, या तो वो जीरो हो या वन टाइम्स या फिर टू टाइम्स ऐसा होना चाहिए वेवलेंथ। दिस लीड्स टू द, और वही है उसी को ब्रैग्स लॉ बोलते हैं जहाँ पे एन लेमडा इज इक्वल टू 2d साइन थीटा होता है। हो 2d साइन थीटा ही हमारा वो हो जाता है पाथ डिफरेंस, ओके, बिटवीन द पाथ डिफरेंस बिटवीन द those interfering x-ray x-rays, the two different rays are meeting at the same point, okay, and if there is no path difference, sorry, if there is destructive interference, then no pattern will be generated. Interference pattern will only be generated in the case of constructive interference. अब देख लेते हैं एक्सरे वन और एक्सरे टू आया, वो थीटा पे रिफ्लेक्ट हो गया, और एक्सरे टू भी आया, वो भी रिफ्लेक्ट हो गया। अब ए बी बी सी, ए बी प्लस बी सी वही तो है, ए बी और बी सी। और ए बी जो है वो बी सी के बराबर होगा, और ये डी है डिस्टेंस बिटवीन द टू एटमिक प्लेन, डिस्टेंस बिटवीन टू एटमिक लेयर्स, टू एटमिक लेयर्स है डी, ओके। तो कंस्ट्रक्टिव इंटरफेरेंस अकर्स ओनली व्हेन पाथ डिफरेंस इज इक्वल टू एन लेमडा, और पाथ डिफरेंस कितना है ए बी प्लस बी सी, ए बी प्लस बी सी इज इक्वल टू एन लेमडा, और एज ए बी इज इक्वल टू बी सी दैट्स वाई टू ए बी इज इक्वल टू एन लेमडा एंड साइन थीटा इज इक्वल टू, और थीटा हमने दिखा रखा है कहाँ है, क्या है थीटा, तो साइन थीटा इज इक्वल टू ए बी अपॉन ओ बी, या ओके, and that is equal to AB upon D, okay, AB is equal to D sin theta, so path difference n lambda is equal to 2D sin theta. This is the condition which needs to be satisfied in order to constructive interference to happen. N lambda should be equal to 2D sin theta, and this is the Bragg's law, okay. X-ray diffraction instrumentation. X-ray diffractometers consist of three basic elements. X-ray diffractometers consist of three basic elements: an X-ray tube, a sample holder, and an X-ray detector. X-rays are generated in a cathode ray tube CRT by heating a filament to produce electrons, accelerating the electrons towards a target by applying a voltage and bombarding the target material with electrons. Copper Cu is the most common target material for single crystal diffraction with wavelength 1.5418 angstrom. These X-rays are these X-rays are what? Collimated. Collimated क्या होता है? अच्छा, कॉलिमेटेड का मतलब होता है समांतरित, मेड एक्यूरेटली पैरेलल। कॉलिमेटेड these x-rays are collimated का मतलब है these x-rays are made parallel to each other. उसमें अगर अगर if those two rays are not parallel, then we will make it parallel by changing the angle of some of the x-rays. Okay, these x-rays are collimated and directed onto the sample when the geometry of the incident x-rays impinging the sample satisfies the Bragg's equation. Impinging का मतलब टकराना, have an effect especially negative one. Strike, impinge means strike. Okay, satisfies the Bragg's equation. Constructive interference occurs and a peak in the intensity occurs. A detector records and processes these X-ray signal and convert the signal to a count rate. Count rate. Okay. A detector records and processes these X-ray signal and converts the signal to a count rate, which is then output to a device such as a computer monitor. The geometry of an X-ray diffractometer is such that the sample rotates in the path of the collimated X-ray beam at an angle theta, while the X-ray detector is mounted on an arm to collect the diffracted X-ray and rotate at an angle 2 theta. The X-ray diffraction instrumentation. X-ray diffraction instrumentation. X-ray diffractometer consists of three basic elements: an X-ray tube, a sample holder, and an X-ray detector. X-rays are generated in a cathode ray tube CRT by heating a filament to produce electrons, accelerating the electron toward the target by applying a voltage and bombarding the target material with electron. Copper's use the most common target material for single crystal diffraction with wavelength 1.5418 angstrom. These X-rays are collimated and directed onto the sample when the geometry of the incident X-rays impinging the sample satisfies the Bragg's equation. Constructive interference occurs and a peak in intensity occurs. A detector records and processes these X-ray signals and converts the signal to a count rate, which is then output to a device such as a computer monitor. The geometry of an X-ray diffractometer is such that the sample rotates in the path of the collimated X-ray beam at an angle theta, while the X-ray detector is mounted on an arm to collect the diffracted X-ray and rotate at an angle 2 theta. Okay. X-ray diffraction instrumentation. X-ray diffractometer consists of three basic elements: an X-ray tube, a sample holder, and an X-ray detector. X-rays are generated in a cathode ray tube by heating a filament to produce electron, accelerating the electron toward target by applying a voltage and bombarding the target material with electron. Copper is the most common target material for single crystal diffraction unit with single crystal diffraction. Okay, single crystal with a wavelength 1.5418 angstrom. These X-rays are collimated and directed onto the sample. ठीक है, collimate X-ray को collimate कर लिया और फिर सबसे पहले प्रोड्यूस किया ही कैसे प्रोड्यूस किया, फिलामेंट को हीट करके, जिससे कि इलेक्ट्रॉन बाहर निकले, और फिर उन इलेक्ट्रॉन को हमने कैसे एक्सेलरेट किया, वोल्टेज अप्लाई करके, और फिर बॉम्बार्ड होने दिया उसको टारगेट मटेरियल पे। हाँ, फिर जो एक्सरे आया उसको हमने पैरेलल किया, और फिर सैंपल पे दिया व्हेन द ज्योमेट्री ऑफ द इंसिडेंट, जब इंसिडेंट एक्सिस का ज्योमेट्री जो कि सैंपल को इम्पिंज कर रहे हैं वो ब्रैग्स इक्वेशन को सेटिस्फाई करेंगे तो हमारा कंस्ट्रक्टिव इंटरफेरेंस होगा। और जब कंस्ट्रक्टिव इंटरफेरेंस होगा तो इंटेंसिटी में पीक आएगा। एक डिटेक्टर होगा जो कि इसको रिकॉर्ड करेगा और एक्सरे सिग्नल को प्रोसेस करेगा और उस सिग्नल को कन्वर्ट करेगा काउंट रेट पे, जो कि आउटपुट आएगा हमारे डिवाइस जैसे कि कंप्यूटर मॉनिटर जैसे डिवाइस पे आउटपुट आएगा। अब अगर हम एक्सरे डिफ्रैक्टोमीटर की ज्योमेट्री देखें तो उसकी ज्योमेट्री कुछ इस प्रकार की होती है कि सैंपल रोटेट इन द पाथ ऑफ द कॉलिमेटेड एक्सरे बीम एट एन एंगल थीटा। अगर सैंपल हमारा रोटेट कर रहा है एक्सरे कोलिमेटेड एक्सरे के पाथ में थीटा एंगल से, वाइल द एक्सरे डिटेक्टर इज माउंटेड ऑन एन आर्म टू कलेक्ट द डिफ्रैक्टेड एक्सरेज, जबकि एक्सरे डिटेक्टर को हमने माउंट कर रखा है किसी आर्म पे तो डिफ्रैक्टेड एक्सरेज को कलेक्ट करने के लिए, वो 2 थीटा से रोटेट कर जाएगा। ओके 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 ओके। एक्सरे डिफ्रैक्टोमीटर अगर सैंपल थीटा से घूम रहा है तो हमारा डिफ्रैक्टेड एक्सरे को डिटेक्ट करने वाला जो डिटेक्टर है वो 2 थीटा से घूम जाएगा, ये बोल रहे हो तुम। एप्लीकेशन ऑफ एक्सरे डिफ्रैक्शन, एक्सरे डिफ्रैक्शन की हम अब एप्लीकेशन देखते हैं। एक्सरे डिफ्रैक्शन टेक्निक्स अलाउ फॉर द डिटर्मिनेशन ऑफ क्रिस्टल स्ट्रक्चर इन इनऑर्गेनिक, ऑर्गेनिक एंड बायोलॉजिकल मटेरियल। फॉर एग्जांपल द डिटेल्ड एटॉमिक स्ट्रक्चर ऑफ द डबल हेलिक्स पॉलीमर डीऑक्सीराइबोन्यूक्लिक एसिड DNA was famously rebuilt by James Watson and Francis Crick via the X-ray diffraction studies of मॉरिस विल्किंस। एक्सरे डिफ्रैक्शन टेक्निक अलाउ फॉर, ठीक है। तो क्या बोला, अब अगर हम एक्सरे डिफ्रैक्शन के एप्लीकेशन को देखें, एक्सरे डिफ्रैक्शन टेक्निक हमें क्रिस्टल के स्ट्रक्चर को हम मतलब एक्सरे डिफ्रैक्शन टेक्निक का यूज़ करके हम चाहे वो ऑर्गेनिक मटेरियल हो या इनऑर्गेनिक मटेरियल हो या बायोलॉजिकल मटेरियल हो, उसके क्रिस्टल के स्ट्रक्चर को डिटरमाइन कर सकते हैं। जैसे कि एटॉमिक स्ट्रक्चर जो है हमारा डबल हेलिक्स पॉलीमर, मतलब DNA के डबल हेलिक्स पॉलीमर डीऑक्सीराइबोन्यूक्लिक एसिड के डबल हेलिक्स पॉलीमर के एटॉमिक स्ट्रक्चर को बहुत ही डिटेल्ड स्ट्रक्चर हमने नहीं पता किया, वो जेम्स वाटसन और फ्रांसिस क्रिक ने पता किया था। वो मॉरिस विल्किंस ने जो एक्सरे डिफ्रैक्शन से स्टडी किया था, मॉरिस विल्किंस ने जो एक्सरे डिफ्रैक्शन किया था उसी को देख के जेम्स वाटसन और फ्रांसिस क्रिक ने रिबिल्ड किया एटॉमिक स्ट्रक्चर, मतलब DNA के स्ट्रक्चर को। ओके, जो भी X-ray diffraction technique allow for the determination of crystal structure in inorganic, organic and biological material. For example, the detailed atomic structure of the double helix polymer deoxyribonucleic acid DNA was famously rebuilt by James Watson and Francis Crick via the X-ray diffraction studies of Maurice Wilkins. Okay, Maurice Wilkins के द्वारा किया गया X-ray diffraction techniques, X-ray diffraction studies को देख के इन्होंने जेम्स वाटसन और फ्रांसिस क्रिक ने फिर से बनाया है डबल हेलिक्स पॉलीमर डीऑक्सीराइबोन्यूक्लिक एसिड के एटॉमिक स्ट्रक्चर को। अब हम देखते हैं स्पेक्ट्रोस्कोपिक टेक्निक्स। स्पेक्ट्रोस्कोपी इज द स्टडी ऑफ इंटरेक्शन ऑफ इलेक्ट्रोमैग्नेटिक वेव्स एंड मैटर। ओके, it normally involves using a specialized piece of equipment called a spectrometer to record the wavelength of electromagnetic radiation to get information about the structure and other properties of the sample. These methods are based on atomic absorption, atomic emission, or atomic fluorescence. A system can undergo a transition between two states 1 and 2 if the energy of the electromagnetic radiation absorbs equal the energy difference between the two states. Delta E1 from 1 to 2 is equal to E2 minus E1 is equal to h nu. On the other hand, emission of radiation is due to the return of an atomic or molecular system from an excited state to a lower energy state, and the energy of the emitted radiation also corresponds to the energy difference between the states involved in the transition. When the system was at a state E1 and it absorbed the energy h nu and reached the state E2 where h nu was the energy h nu was equal to the energy difference between these two states, that is E2 minus E1. and the system was at higher state E2, and it radiates the energy h nu, which was equal to the energy difference between these two states, and then it came to E1. So absorption and emission both are happening. Fluorescence is the process that light that first consumes photon and puts the atom or molecule in an excited state, and then emits a photon of lower energy which takes the atom or molecule back to the ground state. This is known as fluorescence. हम देख लें ground state and then excited state levels. Emitted fluorescent light, when it will emit, emission will happen. First absorption will happen, then emission will happen. The three basic types of spectroscopy are atomic absorption spectroscopy, AAS. This includes methods such as infrared spectroscopy and ultraviolet visible spectroscopy. Atomic emission spectroscopy, AES. Nuclear magnetic resonance, NMR spectroscopy, and X-ray spectroscopy. And then atomic fluorescence spectroscopy, AFS. And in AFS we have Raman spectroscopy. Different methods of spectroscopy may be employed depending on the type of sample and analysis needed. Like we have wavelength range and frequency range. Wavelength in nanometer, 10 to the power minus 5 nanometer, 10 to the power minus 1 nanometer. The gamma rays lies between 10 to the power 24 hertz to 10 to the power 22 hertz. Okay, and the wavelength frequency of gamma rays lies between 10 to the power 22 hertz to 10 to the power 24 hertz, and wavelength of gamma rays lies between 10 to the power minus 3 nanometer to 10 to the power minus 5 nanometer, and frequency of X rays lies between 10 to the power 20 hertz to 10 to the power 18 hertz. And the wavelength of X-rays lies between 10 to the minus 3 nanometer to 1 nanometer. Radio waves lies between 10 to the power 2 to 10 to the power 4. Frequency of radio waves lies between 10 to the power 2 to 10 to the power 4 hertz, and wavelength lies between 10 to the power 3 meter, rise around 10 to the power 3 meter. Then microwave lies between 10 to the power 6 to frequency of microwaves 10 to the power 6 to 10 to the power 8 hertz, and wavelength 1 meter to 10 to the power 6 nanometer. Infrared 10 to the power 12 to 10 to the power 16. And then visible light range the wavelength of visible light lies in between 400 to 700 nanometer. Okay. अब हम देखते हैं infrared spectroscopy. Photons in the infrared region of the electromagnetic spectrum have characteristic energies corresponding to those of molecular vibrations. This means infrared spectroscopy currently remains the primary tool to study the vibrational and rotational modes of molecules. Infrared spectrometer typically measures the relative absorption of different frequencies in the infrared region by a sample. This absorption spectrum can then be used to identify the types of molecular bond present in the sample, indicating the type of molecule structure present in a sample. Infrared spectroscopy. Photons in the infrared region of the electromagnetic spectrum have characteristic energies corresponding to those of molecular vibrations. This means that infrared spectroscopy currently remains the primary tool to study the vibrational and rotational modes of molecules. Infrared spectrometer typically measures the relative absorption of different frequencies in the infrared region by a sample. This absorption spectrum can then be used to identify the types of molecular bonds present in the sample, indicating the types of molecules present, molecular structure present in a sample. Okay, then we will see ultraviolet visible spectroscopy, UV vis for visible spectroscopy. The ultraviolet and visible regions of the electromagnetic spectrum corresponds to electron energy level transitions in atoms and molecules. UV visible spectroscopy can therefore be used to probe the electronic structure of molecules in a sample, subsequently enabling identification of the compounds present. UV visible spectroscopy is particularly useful for identifying peptide bonds, certain amino acids, side chains, and certain prosthetic groups and coenzymes. Ultraviolet visible spectroscopy. The ultraviolet and visible regions of the electromagnetic spectrum correspond to electron energy level transition in atom and molecule. UV visible spectroscopy can therefore be used to probe the electronic structure of molecules in a sample, subsequently enabling identification of the compounds present. UV visible spectroscopy is particularly useful for identifying peptide bonds, certain amino acid side chains, and certain prosthetic groups and coenzymes. Then nuclear magnetic resonance spectroscopy, NMR spectroscopy. Nuclear magnetic resonance spectroscopy is a technique used to measure magnetic fields that exist around atomic nuclei. Okay, NMR spectroscopy uses radio waves to excite atomic nuclei in a sample. When nuclei starts to resonance, this is detected by sensitive radio receivers. As the resonance frequency of an atomic nucleus depend on the electronic structure of the molecule of which it is a part, NMR spectroscopy provides detailed information about the structure and reaction states of molecules. It is hence a powerful tool for deducing the exact nature of monomolecular organic compound. And nuclear magnetic resonance spectroscopy, NMR spectroscopy. Nuclear magnetic resonance spectroscopy is a technique used to measure magnetic fields that exist around atomic nuclei. NMR spectroscopy uses radio waves to excite atomic nuclei in a sample. When nuclei start to resonance, this is detected by sensitive radio receivers. As the frequency response of the atomic nucleus depend on the electronic structure of the molecule of which it is a part. NMR spectroscopy provides detailed information about the structure and reaction state of molecules. It is hence a powerful tool for deducing the exact nature of monomolecular organic compound. Okay, now X-ray spectroscopy. The use of X-ray spectroscopy began with the development of X-ray crystallography. The use of X-ray spectroscopy began with the development of X-ray crystallography in 1912. Father and son team, father and son team, William Henry Bragg and William Lawrence Bragg, showed that diffraction pattern created by X-rays passing through a crystalline material could be used to deduce the nature of the crystal structure. The use of X-ray spectroscopy began with the development of X-ray crystallography in 1912. Father and son team, William Henry Bragg and William Lawrence Bragg, showed that diffraction pattern created by X-ray passing through crystalline material could be used to deduce the nature of crystal structure. Two other X-ray spectroscopy techniques which are commonly used today are wavelength dispersive X-ray spectroscopy WDXS and energy dispersion X-ray spectroscopy EDXS. Both technique enable elemental analysis by measuring characteristic X-rays within a narrow region of the spectrum. Okay. Both techniques enable elemental analysis by measuring characteristic X-rays within a narrow region of the spectrum. Raman spectroscopy. Raman spectroscopy is solely concerned with the inelastic scattering of photons known as Raman scattering, where the apparent wavelength of a photon is changed when it interacts with the sample. This is virtual energy state, and this is vibrational energy state 0, 1, 2, 3, 4. Um, uh, when 0 to these are transitions happening when it is going from 0 to first virtual state and then coming back to 0. This is Rayleigh scattering, also known as elastic scattering, when it is going from 0 but coming to 1. Stokes Raman scattering, when it is going from 1 to the highest one and then coming to the 0. It is anti Stokes Raman scattering. One is Stokes Raman scattering, other is anti स्टोक्स रमन स्कैटरिंग, इन स्टोक्स में 0 से नीचे वाले में, फिर वहाँ से 1 पे, और एंटी स्टोक्स में 1 से ऊपर वाले और फिर ऊपर वाले से 0. एंटी स्टोक्स रमन स्कैटरिंग एंड स्टोक्स रमन स्कैटरिंग, ये these are known as inelastic scattering, and that was and Rayleigh scattering is known as elastic scattering. Raman scattering uses a source of monochromatic light that is used to illuminate the sample. When the laser light interacts with molecular vibrations or other excitation in the molecular system, the energy of the photons is shifted either up or down. Accurate measurement of these energy shifts enables a detailed analysis of the types of chemical bonds present in the sample. Raman scattering provides similar yet complementary data to infrared spectroscopy, IR spectroscopy. Okay. Now, microscopic techniques. Microscopy is the technique to examine samples and substances that are not visible to the naked eye due to their diminutive size. The three main microscopic techniques commonly used are optical microscopy, electron microscopy, and scanning probe microscopy. Okay. Diminutive. Diminutive means extremely or unusually small, छोटा. Okay. कहा था, where is diminutive? Microscopy is the technique to examine samples and substances that are not visible to the naked eye due to their diminutive size. The three main microscopic techniques commonly used are optical microscopy, electron microscopy, and scanning probe microscopy. Optical microscopy, this is the most common and well known type of microscopy and involves magnifying the image of the object by passing light through or reflecting light of it. Okay, by passing light through or reflecting light of it, and then examining this light through a single or multiple lenses. Okay, there are a wide variety of subdivisions of optical microscopy. Mention can be made of bright field, dark field, oblique illumination, fluorescence, phase, contrast, confocal, deconvolution, differential contrast, क्या है ये, and dispersion staining microscopy. Yes, where was I? This is the most common and well known type of microscopy and involves magnifying the image of the object by passing light through or reflecting light of it, and then examining these light through a single or multiple lenses. There are a wide variety of subdivisions of optical microscopy. Mention can be made of bright field, dark field, oblique illumination, fluorescence, phase, contrast, confocal, deconvolution, differential interference, contrast, and dispersion staining microscopy, Okay, and then electron microscopy. This is a form of microscopy that uses electron beams to create an image of the object being used. They have much higher magnification than optical microscopy and hence a much higher resolution. As a result, this allows us to see smaller specimens in greater detail. The resolution is able to be increased because as the electron travel faster, their wavelength becomes shorter. So there is a direct correlation between reducing wavelength and increasing resolution. The subdivisions of electron microscopy are scanning electron microscopy, SEM, transition electron microscopy TEM, scanning transmission electron microscopy STEM, and focus ion beam microscopy FIB. Okay. Then scanning probe microscopy differs from other types of microscopy in that in that rather than rather than seeing the image, the instruments feels it by probing each instrument feels it by okay, instrument feels it by probing each surfaces and sending data to a computer from which the image can be created. The major disadvantage of scanning probe microscopy are: small structure can be created as as the interaction can be modified from the probe, and unlike electron microscopy we do not need a vacuum. Major advantages of a scanning probe microscopy are: small structures can be created as the interaction can be modified from the probe, and unlike electron microscopy we do not need a vacuum. Whereas the disadvantages are: maximum image is generally small, and the detail this shape can be hard to distinguish because of the scanning tip. The subdivisions of a scanning probe microscopy include atomic force microscopy AFM, scanning tunneling microscopy STM, and near field scanning microscopy NFS. इसका कोई शॉर्ट फॉर्म नहीं दिया ना, नियर फील्ड स्कैनिंग ऑप्टिकल माइक्रोस्कोपी, ठीक है. द सब डिविजन्स ऑफ स्कैनिंग प्रोब माइक्रोस्कोपी इंक्लूड्स एटमिक फोर्स माइक्रोस्कोपी AFM, स्कैनिंग टनलिंग माइक्रोस्कोपी STM, and near field scanning microscopy. Okay. And then super resolution techniques. A number of factors can affect the quality of an image, with the most common being suboptimal photographing conditions, lens properties, and post processing artificate artification na artificate. Okay. A number of factors can affect the quality of an image, with the most common being suboptimal photographing suboptimal photographing suboptimal photographing conditions, lens properties, and post processing artification. Another factor that can affect image quality is resolution. More specifically, low resolution images contain a low number of pixels representing an object of interest, making it hard to make out the detail. This can be either because the image itself is small, or because an object is far away from the camera, thereby causing it to occupy a small area within the image. Considering a high cost and the limitation of resolution enhancement through hardware techniques, especially for large scale imaging devices, signal processing methods, which are known as super resolution, have known a potential way to obtain high resolution images. With super resolution methods we can go beyond the limit of the low resolution observations rather than improving the hardware devices. Super resolution is a technique which reconstructs a higher resolution image or sequence from the observed low resolution images. If multiple images of the same scene with what if multiple images okay if multiple images of the same scene with sub-pixel misalignment can be acquired, the complementary information between them can be utilized to reconstruct a higher resolution image or image sequence. Sub super resolution is a technique which reconstructs a higher resolution image or sequence from a observed low resolution images. If multiple images of the same scene with subpixel misalignment can be acquired, the complementary information between them can be utilized to reconstruct a higher resolution image or image sequence. जैसे कि हमारे पास 9 पिक्सल्स थे, सर्कल सर्कल सर्कल, एंड देन 9 पिक्सल्स थे ट्राइंगल ट्राइंगल ट्राइंगल, देन 9 पिक्सल्स थे स्क्वायर स्क्वायर स्क्वायर। इन सब से इंटरमीडिएट हमने एक इमेज बनाया जिसमें कि सर्कल भी है, ट्राइंगल भी है, स्क्वायर भी है। उसके बाद उसको और प्रोसेस किया तो हाई रिजोल्यूशन इमेज उधर हमारे पास तैयार हो गया, जहाँ पे कि हेक्सागोन हेक्सागोन पिक्सल बन गया। ये हमारा लो रिजोल्यूशन इमेज ऑफ द सेम सीन विथ सब पिक्सल अलाइनमेंट था। सेम सीन का लो रिजोल्यूशन इमेज था विथ सब पिक्सल मिस अलाइनमेंट। सब पिक्सल मिस अलाइनमेंट अलाइनमेंट ओके, विथ सब पिक्सल अलाइनमेंट था। ओके, सब पिक्सल अलाइनमेंट था। द 5 डिफरेंट सुपर रिजोल्यूशन मेथड्स आर गिवन बिलो। पहला है जो 5 डिफरेंट सुपर रिजोल्यूशन मेथड्स आर गिवन बिलो। स्ट्रक्चर्ड illumination microscopy SIM, stochastic optical reconstruction microscopy STORM, STORM, stochastic optical reconstruction microscopy, photo activated localization microscopy PALM, photo activated localization microscopy, stimulated emission depletion STED, and 4 pi microscopy, structured illumination microscopy SIM, stochastic optical reconstruction microscopy STORM, photo activated localization microscopy PALM, stimulated emission depletion STED, 4 pi microscopy. Now SIM uses polarized light sources like lasers filtered through diffraction grating, grating. The orientation of the grating is the orientation of the grating is changed several times, and the resulting multiple images used to used to reconstruct an image with better resolution than any of the originals. The points of light which would normally interfere with their neighbors are excited and captured at different times. This allows 100 nanometer XY resolution and 300 nanometer Z resolution. Due to the gentle nature of the technique and speed, SIM represents an ideal method for the imaging of live cells and small organisms. SIM's major disadvantage is that the resolution is only approximately twice that of confocal microscopy. However, it rapidly images very large areas. Okay, SIM uses polarized light source filter lasers filtered through diffraction grating. The orientation of the grating is changed several times, and the resulting multiple images are used to reconstruct an image with better resolution than any of the originals. The points of lights which would normally interfere with their neighbor. The points of lights which would normally interfere with their neighbor are excited and captured at different times. This allows 100 nanometer XY resolution and 300 nanometer Z resolution. Due to the gentle nature of the technique and speed, SIM represent an ideal method for the imaging of live cells and small organisms. SIM major disadvantage is that the resolution is only approximately twice that of confocal microscopy. However, it rapidly images very large areas. Okay, now SIM is done. Now STORM, stochastic optical reconstruction microscopy. Okay, Storm is stochastic stochastic optical reconstruction microscopy. In this method, fluorophores, fluorophores that randomly light up with an image, allowing for the reconstruction of a single image from a large number of images with a sparse labeled with a sparse labeling. Since the sample is sparsely labeled, it is unlikely that two nearby molecules will emit light at the exact same time. Since the sample is sparsely labeled, it is unlikely that two nearby molecules will emit light at the exact same time. In this way, the software can more accurately determine the location of a molecule and reconstruct an image with 10 to 55 nanometer resolution in the XYZ in the X, Y, and Z. In this way, the software can more accurately determine the location of a molecule and reconstruct an image with 10 to 55 nanometer resolution in the X, Y, and Z. The acquisition takes several minutes per image. The acquisition takes several minutes per image, and some dyes are able to blink. Recent advantages have made it possible to utilize storm with live cell imaging, but it is not ideal for highly dynamic processes or experiments that run for long durations. The acquisition takes several minutes per image, and only some dyes are able to blink. Recent advantages have made it possible to utilize a storm with live cell imaging, but it is not ideal for highly dynamic processes or experiments that run for long durations. Then we will see palm, photo activated localized microscopy. Palm is in the same family as a storm, as they both are blinking fluorophores as well as multiple images to create a single image. Palm is in the same family as a storm, as they both are use blinking fluorophores as well as multiple images to create a single image. The difference between the two is that a storm uses dyes while palm uses photoactivable fluorescence proteins. The high end density of light needed for many frames means that palm is not ideal for dynamic processes. ठीक है. The difference between the two is that a storm uses dyes while palm uses photoactivatable fluorescent proteins. The high end density of light needed for many frames means that palm is not ideal for dynamic processes. STED, stimulated emission depletion. S- STED allows to illuminate a spot approximately 200 nanometer wide. The difference with a laser scanning confocal is that a donut shaped red light is projected onto the same spot, turning off all the fluorophores except for a very small area in the center of the whole of the donut shaped beam, because the microscope knows exactly where a point of light came from. The researcher can from the researcher can achieve superior resolution. Some experts with ideal samples can achieve a resolution of just a few nanometer, but it is more realistic to expect a 30 nanometer resolution. Since this method is just an extension of the laser scanning confocal, it pairs well with live cell imaging. Okay. Now then, 4 pi microscopy. Uh, 4 pi microscopy is used for the increase of an image axial resolution. Normally, the axial resolution is about 500 nanometer due to the structure of the point spread function.
With 4-pi microscopy, two objectives are utilized on either side of the sample, and only the illuminated part of the sample which is in focus for both objectives is kept. Thus, the resolution in the z direction is about 100 to 150 nanometer. This technique is very useful for thicker samples like spheroids that can get severely distorted in the z direction using conventional confocal microscopy. अब हम देखेंगे एप्लीकेशंस ऑफ सुपर रिजोल्यूशन टेक्निक. सम applications of super resolution technique in our daily life which are of more basic concern are as follows: regular video information enhancement. Lower resolution video images can be converted to high definition images using high definition image by use of this super resolution technique. Hitachi Limited achieved the conversion of standard definition television to standard standard definition television to high definition television using super resolution techniques, which makes super resolution microscopy technique. Medical diagnosis. Super resolution technique have been used with key medical modalities including magnetic MRI, functional MRI, and position emission tomo position imaging tomography, position imaging tomography. The goal is to increase the resolution of medical images while preserving the true isotropic 3D imaging. Medical imaging system can be operated under highly controlled environments, and thus continuous and multi-view images can be easily acquired. Acha. Biometric information identification. Super resolution is also important in biometric recognition, including recognition enhancement for faces, fingerprint, and iris images. The resolution of biometric images is pivotal in the recognition and detection processes to deal with the lower resolution observation. A common approach is the development of high quality images from multiple lower quality images using super resolution using super resolution. The details of the shapes and structural texture are clearly enhanced while the global structures is effectively preserved, which can improve the recognition ability in the relevant applications. Okay, done.